Hi everyone. So today we are going to have a practice session for the Markov chain modeling. Okay. So all of the problem sets that we are going to discuss for today would be very simple, but it's very fundamental stuff. So let's see what problem sets we have. Okay, here's the first problem. So we just suppose that the chance of producing a defective item is totally depends on the conditions of the previous item that you checked. Which means if the previous item was good, then the probability of producing a defective item would be 2%. But if the previous item was defective, then there is an 85% of chances that the next item will also be defective. Okay? That's the only condition given. Now, given this condition, you are required to sketch the transition diagram that shows the states and the transitions and the corresponding transition probabilities. Okay? So let me give you like 2 minutes. Why don't you think about this? Okay, so, if we say that the process is in state 1, for example, when the item is good, okay, and the state number 2, when the item is defective, then this is a two-state Markov chain, right? Where the transition diagram would be, let's say, okay, here. We have 1 and 2 like this. So this stands for good item and defective item. Okay. Then the good to defective is what percentage? 2%. Is only 2%, right? Which means good to good would be 1 minus 0.02. That's 0.98, right? Also, what is this? Defective to defective is given as 85%, right? Which means this should be only 15%, right? So the transition probability should be 2 by 2 matrix, right? 0.98, 0.02, and then 0.15, 0.85. Is that right? It's very straightforward, right? Easy? Okay. So now let's move on to the next question. What is the probability that if the first item is good, and then the next one, which is the second item, is defective? So this is one-step forecast, right? One-stage forecast. So obviously, you're going to use this P matrix to answer for this question, right? So starting from good, so this is good and defective, good and defective, right? So starting from good, and then you land on defective. So you are looking at this probability, right? Which is 1, 2, which is only 2%. 2%. Right? Right. Very easy, right? Okay, then what about this? What is the probability that if the first item is defective, the second item is also defective? So we need to look at this, right? Which is 85%. How about this? Question number D. What is the probability that if the first two items are defective, then the third item is defective?
So it's p squared.
Why is p squared?
Because there is 2 stages. No. We calculate first of all that one defective by given one defective, and then by.
Okay, that is a good thinking. Is there any other opinion? What property do we have to use here? Markovian property. Memory is property. Okay? So, although they consider the first two items, we are not interested in the first item. Okay? We just want to see the second item. Okay? The condition of the second item among these two. Okay? So, starting from second item is defective, we want to know what is the probability that the third item becomes defective. Okay? So it's like same as this, right? This is exactly the same. Is that right? Which is P22. That is 85%. Because Markov chain has a memories property. Okay? Just be careful. Okay. Okay, now how about question E? What is the probability that if the first item is good, then the third item is defective? So which information do you have to use? So this is the two-stage forecast, right? Which means we need p-square matrix. How do you get p-square matrix? Just p times p, right? Which is 0.98 times 0.98, 0.02, 0.15, 0.85 times same p matrix 0.98, 0.02, 0.15, 0.85. Right? Okay, let me. I don't know why it's frozen. I cannot. I don't know why I cannot control this. Okay, anyway, does anybody got this p-square matrix? let me get this. So this is going to be, let's say this is A, B, C, D. Then how'd you get A, for example? That's going to be the first row times the first column, right? So 0.98 times 0.98 plus 0.02 times 0.15. That goes to here. How about B? That's going to be first row times second column. Likewise, C can be obtained by multiplying the second row and the first column. Likewise, D can be obtained by multiplying the second row times second column, right? Okay, so I have 0.963. Okay, thank you. Is that 0.0336? Okay, but let's use 37 so that the summation of this first row becomes 1. Okay. How about this? It's 0.275. 0.725. Okay. So this is the p-square matrix. So using this p-square matrix, how do you answer this question E? That's going to be 1, 2, right? Starting from good, and then after 2 items, it becomes defective. So that's going to be this, right? Only 3.7%. Okay, how about the last question? What is the probability that if the first item is defective, the third is also defective? Again, we do need p-square matrix, right? And then this time, starting from 2, and you end up with 2, state number 2, which is 72.5%, right? Any questions? It's very easy, right? Okay. Okay, and just to let you know, for the next 3 problems, were extracted from one of the reference book that I've listed in our syllabus, which is the Introduction to Product Probability Models by Dr. Sheldon Ross. So again, let me give you a couple of minutes. So why don't you read through the problem number 2 and problem number 3 together, actually, yeah, because we can handle both problems number 2 and 3 at the same time. So why don't you read through problem number 2 and number 3, and then think about how you can handle this. Oh, I got it. Okay, I was in the reading mode, so I was not able to edit the documentation. Now I got it. Okay, so now I can control. So in these two problems, we assume that there are only two different weather conditions each day, right? Rains or not rain. Okay. So how many states are needed? How did you define the state of system? Okay, so I'm going to use, let's say, okay, I'm going to use maybe, okay, not like, okay, like this. Let's say, and R. So for example, if I say like this, if I define the state of system, for example like this means that it is raining today, okay? And then it was not rain, okay, yesterday. And then no rains the day before yesterday. Okay, so we have include the weather condition for 3 consecutive days. Okay, the weather condition for the 3 consecutive days. This is what happened the day before yesterday. This is what happened yesterday, and then this is today's weather. Okay, so how many states are needed if I define the state of system in this way? 6? You got to be careful because for each day, how many different possibilities? 2 different possibilities, right? So 2 times 2 times 2 is 8, right? So we're going to have 8 different states if I define state of system in this way. Is that right? So using the state of system this way, let's build up our transition probability matrix. So this time I'm going to consider all of these given probability values. Okay? So I have huge matrix. Maybe let's draw the transition diagram first. Probably that'll be easier because for me at least drawing the transition diagram would be better. So let's say so we have 8 different states. So let's say R, R, R. That's our very first state. Okay, and then say R, R, no rain, and then rain, no rain, rain, and then rain, no rain, no rain, and then no rain, 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 and no rain, rain, no rain, and no rain, no rain, and then rain, and then finally no rains over 3 days. Okay, so we have 8 different states this way. So starting from this state, we had rain for 3 consecutive days. What transitions occur? Of course, we're going to have this transition, right? What is this? 0.8, right? Because of here, if it has rained for the past 3 days, then it will rain today with probability 80%, right? Okay. Then what other transitions do we have starting from this state? We have this transition, right? That's going to be 0.2, 20%. Because there will be no other transitions starting from this state. Okay? We never have those transitions. Why is that? When you draw the transition diagram, in this case, you have to be careful. You need to match these two weather with these two weather all the time. Okay? Because we have the starting point, we have raining for the last 2 days, which means if you want to draw a transition diagram, you're going to make sure for the first 2 days there should be raining, right? But because in the second day it's not rain, so we cannot have this transition, right? Okay, now starting from here, what transitions do you have?
So is it 0.6 from
So, yeah, so again, in this case, you need to make sure this Rn appears Rn in the first 2 days weather, right? Again, here we have Rn that does match here, so, which means we're going to have transitions occurs. All right? What is this? Okay, it does say in any other case the weather today will with probability 0.6, 60%. So rain today. Okay. Okay, so we're going to have 60% down here, right? Which means this got to be only 40%. Now we're going to start from here. So we're going to match these two letters, no rain and rain. If you look at this, the first 2 letters, we have no rain and rain. Also we have down here, no rain and rain, which means we're going to have this transition occurs and this transition occurs. Okay? Let me put down here 0.6. So this time we have 0.6 and then 0.4. So you just need to continue on this. Starting from here, what transitions occur? Now we need to match these 2 characters, no rain and no rain, for the last 2 days. So after 1 day, we have no rains down here and here, right? So we're going to have this transitions and this transitions as well. This time this is going to be 0.6 and 0.4. Is that right? So this diagram, transition diagram, would be very complicated in the end. So if you want to keep going, now we start from here. We need to look at this. And then you see that the first two characters here, raining and raining. So we're going to have these two transitions, right? So this is going to be 0.6 and 0.4. So you need to complete, taking consider all the other threes, okay? The same way. So I'm gonna construct the one step transition probability matrix based on that. Okay, that's going to be P matrix. So we have big matrix. So I'm going to say here R, 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 no, R, no, R, rain, no rain, no rain, and then no rain, 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 no rain, rain, no rain, no rain, no rain, rain, and then no rains. So I'm going to copy the same up here. So five, 6, 7, and then no rains for the last 3 days. And we have here 0.8, 0.2, and then down here we have 0.4, 0.6, and then down here we have 0.6, 0.4, and we have 0.4, 0.6. Okay. So far we have like this. Okay. Then, okay, now we start from no rains the day before yesterday, and then rains yesterday and today. So we have 0.6, 0.4, and down here we have 0.4, 0.6, and then we switch over 0.6, 0.4, and down here we have 0.2 and 0.8. Okay? So This is the one stage, one step transition probability matrix. Okay. Any questions? We've done very similar problem once before, right? Right now we are dealing with 3-day forecast in one state. But last time we included 2-day information within one state, right? So this is the little bit of extended version of that, but it should be okay for everyone. Okay, now let's move to the next problem. Do you need more time? Okay. Again, this problem is from the Sheldon-Ross Introduction to Probability Models textbook. So in this problem, 3 out of every 4 trucks on the road are followed by a car, while only 1 out of every 5 cars is followed by a truck. Then we want to know what fraction of vehicles on the road are trucks. Of course, first step is to define the state of system, and then based on that, we need to build up our Markov chain model, right? And then, what are you going to do? We're going to determine steady-state probabilities distributions. After that, we should be able to answer for this question. Okay? So if I say, let's say, oh, what did I do? Okay. So if I say x of n is 0 if the nth vehicle is a car. If the nth vehicle is a car, and let's say x of n is equal to 1 if the nth vehicle is a truck. Then again we can build up two-state Markov chain model, right? So what are you going to have? One step transition probability matrix. It's going to be like this. So here, 3 out of every 4 trucks on the road are followed by a car. So it does say 3 out of 4 trucks, right? So followed by a car. Does that make sense? So that's why I put 3 over 4. And then here, only 1 out of every 5 cars are followed by a truck. So where do you want to put 1/5? Up here, right? Because only 1 out of every 5 cars, right, is followed by a truck. And because summation of each row has to be equal to 1, this is simply 4 out of 5, and then 1 out of 4. Is that right? Does that make sense? So again, defining the state of system is very important, right? If you define the state of system, then the next step is very easy to do. Not always, but okay, most of the time. Now we need to determine the steady state probability distribution. Since we have only 2 states, so we're going to have pi 0 and pi 1, right? Pi 0 would be pi times the first column of this P matrix, because we are going to use pi equals pi p in a matrix form, right? That's going to be 4/5 pi 0 plus 3/4 pi 1. Likewise, pi 1 would be pi times the second column of P matrix. So 1/5 pi 0 plus 1/4 pi 1. Is that right? However, these two systems of linear equations are linearly dependent. So you're going to arbitrarily choose one of these equations and then discard it. Instead, we are going to add another constraint, saying that pi 0 plus pi 1 is equal to 1. Okay? So using these two equations, you should be able to compute and obtain the steady state probability distributions. So the easiest way is here from the second equation. You see that pi 1 is 1 minus pi 0. And then we're going to use this to the first equation. Right? That's what I did earlier. And from my previous computation, I have pi 0 is 15 over 19, and then pi 1 is 4 over 19. Do you have the same answer? Okay, good. So how do you answer for this question? What is the answer? What was the question? Okay. What fraction of vehicles on the road are trucks?
Pi 1.
So the answer is pi 1, right? So I do answer 4 out of every 19 vehicles is a truck. Okay? That is our answer for this question. Easy, right? Okay. Okay. Now I'm going to distribute another problem set. This problem is very similar to what we've done last time. That is about the SS inventory problem. Both cases with and without considering back orders. So and you will find that this problem is about the same as what we discussed. I just changed the numbers: probability distribution, demand distribution, and real point, and the maximum inventory levels. Okay, so this would be a good practice problem for you while preparing for the exam next week. So
It's going to be inventory was included.
you're right. So everything will be included for the midterm exam until today's lecture. Okay. And we're gonna post the solution, although this is very easy to do, but on our Canvas system later. So it's up to you. Since we have plenty of times left today, probably we're gonna end the recording right now, but I'm gonna stay here. If you need, let me know. Okay. If you need some help while constructing the one-step transition probability matrix, just let me know. Okay? Because I say this inventory control problem is quite important in our lecture. So make sure you understand how to derive those transition probability matrix. Okay? Okay, so Raman, could you end the recording for today here?
Yes, sir.
Okay, thank you.